Hey everyone, welcome to the first video. This is our first lecture informally, and we're going to have many going on from this, and then we'll get to talk in person. But this first one is going to be on logic and sets. It's going to be our introduction into these lectures on math before we get into the physics. And before I get into the actual topic, I want to talk about what math is going to be like for us compared to what you're used to. So, for the most part, the math that you've learned about has focused on two things. So, one is either problem solving, so you're solving specific problems that many people don't see the motivation for, and I would agree. Most times I don't see the motivation for. Um, but for some people, problem solving is fun. And the other is primarily modeling. So modeling some sort of phenomena, whether that's physical or um, statistical or just some sort of quantitative thing, modeling that mathematically. And these are the two biggest things that you've talked about in math in school, and they have a lot of intersection with each other. I think since you're interested in physics, you probably know that. But this isn't really the full picture of what math is like. So, to get an idea of what math is really like, there's this professor at UPenn. His name is Po Shen Lo. He has this really nice quote where he says, "Math is the heart of understanding." And I think for someone who really loves math and abstract math, who has a hard time trying to really eloquently put what math is like, I think that is the perfect way to say it. Math it's really about trying to find what's true fundamentally, and more importantly, understanding why. It's not about solving specific problems, solving specific algebraic equations, or, you're familiar with calculus now, of solving problems in calculus and stuff like this. That's not what math is about. It's about trying to figure out what is true about nature from sort of these first principles, and also understanding conceptually why that is true, and trying to find the underlying patterns and structure to these statements. Okay, so that sort of brings us around to logic and sets, because they form the groundwork for how we actually make progress in math and talk about math. So if we start out with logic, logic is really, very similar to math. One might consider them one and the same. Logic is a very big field of research in math. It's about trying to figure out what is true and how to derive new true statements from already true statements that we know about. So, at a sort of fundamental level, we have this idea of propositions, or we might also call them statements, or maybe you'd like to call them claims or something like that, whatever is really easiest for you to think about them this way. The terminology isn't so important. But the point is that these are just things that can be true or not, right? This isn't really a strict definition. We're just trying to do this intuitively. But maybe it's good to think about it this way. Things that can be true, and then, or they can be false, obviously. So, for example, we might say 2 is even. This is a proposition or a statement, and we know it to be true. we might have another proposition where we say 2 is odd, and that would be false, right? These are just simple examples. And so in a more general case, we could write the proposition as P. So if we have a proposition that we call P, then what we're going to say is that if we want to write that P is true, we're just going to write that as P. And this might seem weird, but if you think about these propositions as something like 2 is even, and substituting that for P, then if I write just the proposition itself, 2 is even, then you get the idea that this is just a true statement. I don't need to say 2 is even is true, right? Sometimes I will write out later in all of our lectures, I'll write out a proposition and then say is true just because it reads better that way. But, these are not really things that we should get hung up on, right? As long as the general idea is there, then we should be okay. So from there, we also have essentially the opposite of P, right? So if we want to say, well, this proposition P is actually false, so P is false, okay, well then we'll add this little symbol in front of P. I'll use a tilde. Some people use a minus sign. I think that's confusing for us because we're going to be doing math that involves, minus signs being like actual negatives, and you don't want to get stuff confused. We also won't use the tilde too much anyway, so I guess it doesn't really matter. But formally, this is how we would write this. So this is called the negation of P. And all this means is that if we write this, we're saying that P is false. Okay. So, great. We have these propositions. We can say, we write P, that means P is true. We write this not P is how we would read this. So let me just write that. So this is read as not P, or you could just say P is false. And it's great to have just statements by themselves, but if we just have a set of statements, and if we don't know how to arrive at new statements, then there's not a whole lot we can actually do. So we want to have this idea of deriving new true statements from statements we already know to be true, and to have a sort of symbolic way of expressing this. So we have this idea of a logical implication. P implies Q. So we have this this sort of arrow from P to Q. And this is saying essentially, if P is true, then we can prove that Q is true. Okay, so, I should say, by the way, that a lot of this earlier stuff will probably be a review of things you did in geometry, and that's good. It's good to deal with stuff you're familiar with. So you'll probably remember that you would read this statement as if P, then Q, and that is correct. But I think this way of saying it is a little bit more descriptive and maybe a little bit more accurate. That if P is true, then we can construct a proof of Q, right? And it's going to be, pretty helpful for us because stuff we'll be dealing with involves proofs or something like that, or we'll be using that idea. And additionally, there are situations in which we would like to talk about P and Q being true at the same time or false at the same time or some combination of these. And so we would like a symbolic expression for those as well. So we say that, or we would write P and Q if you're trying to say that that both P and Q are true. So P is true and Q is true. It's pretty self-explanatory. I'll put quotes on these just to show that this is what we would write. And then we have P or Q. And this one, if you're seeing it for the first time, you want to be careful about. If you're a computer science kid, then you probably will get this one. You won't get this one mixed up because you know about AND gates and OR gates and all of that. So this is saying at least one of P and Q is true. Okay, so if you haven't done computer science and logic gates and stuff, then you might think, well, wait, how can both P and Q be true if we say P or Q? Shouldn't it be one or the other? And that's really just an artifact of English. With P or Q, we want to be saying that it is okay if both P and Q are true. There will be situations in math where we really just need one or the other condition to prove a certain statement, but it's not bad if they're both true, right? So we want to allow for that possibility that they're both true. And then, if you're familiar with computer science, you might think, well, oh, we have P XOR Q, just like an exclusive OR. And you could say that, but it doesn't really get used a lot, so we're not going to bother with it. Okay, so we're sort of starting to develop a language here with these propositions. And if we start doing proofs, we'll see how that pays off. There is one last thing I want to say with these new expressions, which is that if it is the case that P implies Q and Q implies P, then we write this as P and then this double arrow Q. Or we also write this as P and this IFF, which is if and only if. So P if and only if Q. Okay. So what does this mean? So, well, from the first part, we're saying that P implies Q and Q implies P. But basically, this is saying that whenever P is true, then Q is true. And whenever Q is true, then P is true. So if we kind of think about this from a process of elimination perspective, if we say P implies Q, P doesn't have to be the only proposition that implies Q, right? We could have a bunch of different propositions that all imply that Q is true. We just know that P is one of those. Okay. But then if Q implies P, that means that that if we have like a proposition that is mutually exclusive to P, then Q cannot imply that, because then you would say P implies Q, but then Q implies something that is not possible when P is true, right? So the idea is that P and Q are sort of logically equivalent in a way. You can't have both P implies Q and Q implies P and then sort of contradict P, or to like have some sort of situation where P and not P happens. Or maybe a better way to say that is that if Q is true, we know that we could never have a situation in which P would be false. Yeah. So, and this is also expressed by the if and only if. So basically, if we say P if and only if Q, basically the first part is saying that if Q, then P. Sorry about that. And the second part is saying basically only if. So there's nothing else that could imply P. So it's basically the reverse of what I just said. Not reverse in sort of the truth, but reverse of the order of P and Q. So we're saying only if, we're saying Q is the only thing that could imply P. And that's basically what I was just talking about before. So that would be equivalent to saying if P, then Q. All right. So this gives us our notion of logical equivalence. Right? Two propositions are logically equivalent if one is true if and only if the other is true. So if you're familiar with the idea of truth values and truth tables, which I don't really want to talk about too much because we're not really going to use them, but if you are familiar with them, then this statement that P is true if and only if Q is true is the same as saying that the truth tables for P and Q are exactly the same. And that's why we say that they're logically equivalent. That's maybe a more visual or quantitative way of looking at it. Right. So in particular, we're going to come across this idea of an equivalence relation later, and I just want to introduce the idea so that it gets a little bit more normalized for you. And that is that we like to consider something an equivalence relation if it has the following properties. And if you think about literal equality that you're familiar with, like 2 equals 2, then you'll see how this kind of should make sense for just normal equality. So we would like to say that P is true if and only if P is true. And hopefully that's pretty obvious. If P is true, then P is true. And the other direction, if P is true, then P is true. Which means that P is true if and only if P is true. So you might remember way back in like green or something. I don't remember when I specifically learned it. But this is called the, let me get this right, the reflexive property, right? Reflexive. And we also have symmetric. So basically, P, actually, let me start using this IFF notation because I will probably use it in the rest of what we do. So P if and only if Q. So this itself should imply Q if and only if P for whatever P and Q that this is true. And I could do both directions on this, but it's redundant because I'm saying it's true for whatever P and Q. Okay. So for the symmetric property, this should make sense because if we want to show that Q is true if and only if P is true, well, this is saying, this is equivalent to saying that Q implies P and P implies Q. And, well, this one is equivalent to saying that P implies Q and Q implies P. So hopefully it's pretty clear that these two things here are equivalent. And if you're really nitpicky and you're asking like, well, why? Like, fundamentally, why is that true? I think it's probably an axiom of logic that, or something like that. Or maybe it's not even an axiom, but if we say A and, or, yeah, let me just use two different ones. If I say A and B, if A and B is true as a proposition, then B and A, or sorry, B and A is true. Okay? But anyway, And then our last one is transitivity, or the transitive property. And this is saying if we have P if and only if Q, and we have Q if and only if R, that is the next letter, the alphabet, then, and I'm using less formal notation right now, but that's okay. Then P if and only if R. Okay, so in a way we're saying, if P implies Q and Q implies R, then P implies R. Right? That's really the important fact that makes this true. And then we can go the other direction as well. Okay, I'm not going to prove this. It should be pretty intuitive. Okay, so we haven't really done much concrete examples with this, and there's a reason for that. But hopefully this makes enough sense. And if it doesn't make that much sense, we're going to, we're going to spend a lot of time with concrete examples with these things, so you'll get a lot more familiarity with it. Okay, so from here on, we're then going to start talking about sets. Okay, so the idea of a set is really just a collection of things. Again, being very vague here like I was with propositions. And these things we call the element of that set. Okay. A bit self-referential, but that's kind of how it has to be. And you're probably familiar with the idea of sets, from the early math that we all did as kids. And we kind of just treated them as like putting numbers into these like categories, or like almost like boxes that you just had like sets of numbers, and it wasn't really clear why or what they were there for, which is kind of sad. And we don't really get the actual point of a set, right? So what I want to encourage you to do is to think about this deeply and try to think of, the world, nature, universe without this concept of a set or sets at all. And it doesn't really make sense to have all of that without the notion of a set. Because if you have this idea of existence or truth, then you have this set of things that exist, or, or even more fundamentally, what it means to exist is to be this element of a set that corresponds to existence. So we're not going to be dealing with sets out of pure wish and desire because, we're going to be classifying and categorizing stuff. We're going to be using sets because there is no other choice. Sets are just fundamental to the world, and they express the existence of things and how they belong to like other things. So that is why set theory is so important, and that's why we have no choice in math but to use sets. Right? It's just talking about what can exist. Okay, off my philosophical soapbox now. Let's talk about some examples just to get us started, to get some familiarity with this. So, you're most familiar with sets of numbers, so we could just say like we have a set S, and we'll say its elements are 1, 2, and 3, let's say. So this is a pretty just normal set. It's finite. It contains these integers. Not super interesting, but it is a set. That is what it is. And so we can have perhaps some more interesting examples where, and this is the fun part of math where you get to draw pretty pictures. You can have the natural numbers, where with sets we like to add these lines to make things look nice. The natural numbers, if you remember, you may have also called them the counting numbers. So they're the positive integers. Sometimes we include 0, sometimes we don't. That's really a convention. I don't remember what's normal in the US for natural numbers, but yeah. We have the integers, which we use z for. I don't remember why we use z for it, but we do. So these are positive integers, 0, negative integers. We have the real numbers, which you should be pretty familiar with. We also have the complex numbers, and a bunch of other stuff, right? Lots of different sets. But sets can also be really abstract, really to any level of abstraction. For example, you can have sets whose elements are sets themselves. And so, we might have an example that this isn't of much practical use, but we could say the set containing 1, and then also the set containing 1 and 2, and then also the set containing 1, 2, and 3, and so on. So we could stop this at some point, or we could just let it go on forever. Either way, this is a set, and the elements of this set are sets. There's nothing preventing us from doing this, right? All we're saying that a set is that it's a collection of things. Those things can have any level of abstraction, right? So it's perfectly fine to call them those things, let them be sets. Or those things themselves can be sets of sets, and it can just go on and on forever. Okay? And to also re-emphasize my point of just sets confer the idea of existence, you can have some set that's like your family members. So I have a mother, I have a father, I have a sister, and me. And I would put their actual names, but I feel like that would be a waste of time. But the point is that it doesn't need to be just numbers. I think one of the biggest confusions about sets when people first encounter them is that they think they're just collections of numbers, and that's not true at all. Not true at all. Sets can contain anything, any level of abstraction or whatever. Okay, so a lot of our practical use of sets will be for classifying different kinds of numbers or some sort of abstract objects. And the reason for that is that if you're talking about a specific set, that gives us context to what we're doing. So if we're doing a certain proof about the real numbers or the integers or something like that, then working within those specific sets, it's giving you information about, the context of the proof that you're doing or the statement that you're proving. Right. So, for example, you might say that for every integer, right? So we might say for every element of z, an element, so this element is always either even or odd. Right? It wouldn't make sense if we said every number is either even or odd, because that's just not true. Like if we said every real number is either even or odd. But it makes sense when we're talking about integers. We have a well-defined notion of what even or odd is for integers. So these sets, they give us context for what we're doing. And so to express that something is an element of a certain set, we would say that, let's say we have a thing, an element x. We want to say that it's in the set A. Let's call our set A. Then we use this symbol that looks almost like an E. So we would write x in A. So we often read this as x in A, or you can say x is in A, or whatever makes the most sense in English in the thing that you're reading. So, for example, you could say the number 2 is in the natural numbers. This is something that is true, right? And of course, usually, sometimes just proving, something like this is useful. Not this specifically, but just that something is an element of a certain set. But most often what this is going to be useful for is talking about what kind of elements you are using in the math that you're doing. So maybe you want to talk about all of the integers or all of the real numbers, or maybe you're working with a specific set with interesting properties and you're talking about all the elements of specifically that set. Or maybe there is some sort of interesting mathematical statement where a certain property is satisfied for at least one element of a set. And you want to say, oh, there exists an element in that set such that this thing is true. Right? So that's also pretty common. So we want to codify these ideas with more symbols. That's what we do in math. We use symbols. So we have this idea that, something can be an element of another set. We write that as this x in A. But we might want to talk about all the elements of that set. So if we want to say for every / for all, I'm also going to put this one because sometimes it's easier for people to understand this, or for each. So we can use any one of these. X in A, or let me use the symbol to get us used to it. So if we want to talk about for every x in A, then we write this as this. So we have this upside down A. Don't know why it's an upside down A, but this symbol just means for all, right? Or for every or for each, whatever makes the most sense to you. So we're talking about all the elements of A, right? For all x in A, and then we have some sort of proposition probably that's, dependent on x, and we're judging whether this is true or not, right? So we might have some interesting proposition that takes in some sort of like a variable. And if we were saying that this whole statement is true, we would be saying that this proposition P is true for all x in the set A that we would put into this proposition. Okay, so what is an example that we might say? Yeah, so we could say, for all x in the natural numbers, x is greater than or equal to 0, right? So this is a proposition, right? X is greater than or equal to 0, and it depends, its truth value, or let me not use that word, its truth depends on x, okay? And if x is in the natural numbers, then we know that x is always greater than or equal to 0. So this statement as a whole, for all x in n, x greater than or equal to 0, that's how we would read it. Let me do this again. This is true. Okay, so let me just say how we would read this. Because learning how to read math this abstract math, it's a skill you have to learn. It's kind of like learning a new language. So for all x in A, P of x, and we could say is true, but remember, sometimes it's just a bit clunky to say is true, but I'll write it for now. Okay. Now, there's the other situation I was talking about where we want to say, there exists some x in A, right? There exists an x in A. And maybe such that P of x is true, right? Maybe this is how we want to read a statement, and mathematically, this is how we would write that. So we have this backwards E. So backwards E, and then have x in A. And then you can choose whether to write this next thing or not. I prefer to do it because it makes it easier for me to read. And some mathematicians also write it. But I put st, which means such that. So I'm saying there exists an x in A such that P of x is true. Okay. So let's think of an example where this makes sense to say. Right. So we could say there exists an x in the real numbers such that, x squared is greater than 0, right? This is true for most real numbers. But the point is that it doesn't have to be true for only one, right? We're saying that there just exists an x in the real number such that this is true, right? So you could think about it as there exists at least one element of the real number such that this is true. Okay? And, you could also say, or actually I might get into that later. Yeah. I think one thing that I left out that I just want to come back to is that we can say the opposite of these things. So I'll talk about just this statement where we say x is an element of A. We can negate that, right? So formally you'd write it as this. But how we're usually going to write this is just x is not in A. So we put a slash through it to indicate that. And we're going to put slash through these other things, but we can understand those in some other ways, and we'll talk about that in the next video. All right. See you guys next time.